Welcome, and thank you for joining me on this webinar about how to tackle separation challenges with advanced asymmetric field-flow fractionation and a discussion about future directions in the technology. I'm Steve Trainoff, and I'm a scientific fellow at Waters Wyatt. I'm going to talk a little bit about how FFF can be made a lot simpler, more accurate, more reproducible, and more accessible to the average user. Let me start with a brief history of FFF combined with multi-angle light scattering. The FFF family of techniques was invented by Kel Giddings in the 1960s, and I say family because there's a large number of different fields can be applied. You can apply a thermal gradient, you can apply an electrical field, you can apply a sedimentation field, but by far the most popular variant is the asymmetric flow FFF that was invented by Carl Gustav Weyland in 1986. In the early 1990s, Phil Wyatt, who was the founder of Wyatt Technology, started a collaboration with Kel Giddings to explore the coupling of FFF and multi-angle light scattering. And the idea is that although the theory of FFF is quite well developed and understood, it ignores things like interactions on the membranes and the three-dimensional effects that happens in the corners of the cell. And so if you use the elution time and the FFF theory to compute back the size, you are limited by these interactions. And Phil Wyatt rightfully pointed out that if you combine it with multi-angle light scattering, then you measure what comes out and not necessarily when it comes out. And that lifts this limitation. And so this would be a very powerful technique. And so we started on some joint installations with FFF with multi-angle light scattering with the spin-off company that Kel Giddings students started called FFF Fractionations. And those instruments were basically the original prototype designs put into the boxes, and they were the highly engineered products that we know today. So it was quite challenging to make this work, even though it was very clear that the coupling had tremendous power. So the next major advancement was in the 2000s when Christoph Johann, who was the founder or the principal of Wyatt Technology in Europe, who developed a version of the FFF technique, asymmetric FFF, called the Eclipse. And he had two innovations. He really eliminated the multi-pump systems that had been used before in favor of a single pump with a series of mass flow controllers that control the downstream flows. And this was spun off into an independent company called Superon. And so for the next 20 years or so, we made light scattering instruments coupled with these FFF systems. And in 2018, the Superon product was products were integrated back into Wyatt Technology. And then we really had an opportunity to start from scratch and think about all of the pain points and how to resolve them to make a truly novel system. And that development effort was called the Neon Eclipse that started in 2020 and sadly was launched during COVID, but it's turned out to be quite successful. And in 2023, Waters acquired Wyatt Technology, and we've modified the system to use the Waters ARC HPLC platform as the chromatography handling system. We added a high-pressure option to allow us to use both FFF and switch to SEC. So I'm going to show you a very simple model where there's two plates that are separated by 500 microns. So here's the bottom plate, and the upper plate would be way up here. And we're going to concentrate on just what happens right near the bottom plate. So you introduce the sample into the channel. And so here's a sample of large particles and a sample of small particles. You apply a field, and with the asymmetric flow, that field is simply the Stokes force pushing down on the particles. The fluid goes through the membrane, and the particles cannot, so they start to pile up or get concentrated near the accumulation wall. Now, whenever you have a high concentration in one location and a low concentration elsewhere, diffusion will act to counteract that, and you'll get a diffusive flux that tries to drive the samples off the accumulation wall. And eventually you'll reach an equilibrium where the field and the diffusion balance each other. And in that case, you'll get a high concentration near the membrane surface, and it'll decay exponentially into the bulk. Now consider what happens when you look at just the big particles. Well, here, because they're large, they feel a large field, a large force from the field pushing downwards. And because they're large, the diffusion constant is small, so the diffusive flux upward is small. And so you end up with a high concentration that decays quite rapidly in the bulk, so the exponential decay constant is quite small. Now, if you do the same type of analysis for the small molecules, Well, the field pushing down on them is going to be small, and the diffusive flux will be large. And so you'll still get a high concentration near the surface of the membrane, but the exponential decay into the bulk will go much further. So on average, the small particles will sit higher up in the channel than the big ones. And now the magic of the FFF fractionation is when you apply a secondary force field along the channel. In this case, it's going to be a Purcell flow, and near the surface, the flow is zero. And as you go progressively further up into the channel, it goes faster and faster. And of course, there's a maximum field way up in the middle of the channel, but we're concentrating on just the bottom surface. And what that means is the big particles that are on average closer to the wall will travel downstream more slowly than the small molecules that on average are sitting further up. And so the net result is the small molecules come out first, and then eventually the larger ones follow them. Now, even though it depends on shear to do this separation, it's intrinsically a very low shear technique. So it's very gentle on the particles, and small or weak aggregates do not break. A quick simulation where the sample is going to be introduced into a channel at one end, and as you'll see, when it's introduced, it basically fills the channel from top to bottom, or from floor to ceiling. And then we're going to push the sample downstream, and the first step is this technique called focusing, where we're going to apply flow from the outlet in and from the inlet down. And it's going to cause the particles to line up on a line. Let's watch the simulation go. It does two purposes. The focus pushes the sample off of the ceiling and gets it all down onto the membrane where the fractionation is going to occur, and it forces the sample, which was originally in a large blob, to basically start a line, like all the runners at the beginning of a starting line of a race. And then you change the flow so that it only goes down through the exit, and now you can see the small molecules are traveling downstream more rapidly than the big ones. And so if we collect them at the end, we're going to see the small molecules and then the big ones. Let's compare this to more traditional chromatography, such as size exclusion chromatography. So here we have a column that's filled with packed beads that are porous. And if you consider three different particle sizes, red being the small and blue being the large, if the beads are porous, then the small particles can diffuse into the pores and back out. Intermediate sized particles can diffuse, but not as far down, and the large ones are effectively excluded, hence the size exclusion. So from the point of view of the small molecules, they see a larger available volume inside this column because they can access all of the small pores and the big ones cannot. So the net result is, if I look at the transition down the channel, they start out co-mixed, and then as they move downstream, they separate, and now the big ones come out first, which is the opposite elution order of FFF. Another difference between size exclusion chromatography and field flow fractionation is this is intrinsically a high shear separation, because these are packed beads and the spacing between the beads are quite small, and the interaction surface for potential stray interactions can be quite large. So FFF is low shear, low interaction surface, and SEC is potentially high shear and high. Why would you care to use one or the other? And there's a strong overlap between the two techniques. The first thing to notice is that SEC works beautifully from a nanometer up to about 50 nanometers or so, and FFF works beautifully in that range as well. Now, if you have two techniques that work well, then why would you use one over the other? And what I usually counsel people is that if SEC works, absolutely use it. It's well established, it's fairly straightforward, it's well understood. So in this range, there's overlap between what FFF can do to SEC, so I would argue use SEC. The real strength for FFF is it has a very wide dynamic range. It can go all the way from 1 nanometer up to a micron or even higher, and it's in this range where we're looking at macromolecular assemblies, we're looking at virus-like particles or liposomes or more complicated structures, and this is where the power of FFF really begins to shine. So I'm going to show you plenty of examples of both SEC and FFF, but remember, the real benefit is going to be in this region where SEC doesn't perform well, but FFF still does. And one of the real strengths of FFF is because it's tunable. we have the ability to control the channel flow and the cross flow, which provides the field, so you can tune it to look at either small molecules or big particles or things that have both. So you can look at molecules and aggregates of those or macromolecular assemblies in a single run. The low shear also has benefits because low interaction with the membrane means that it's relatively safe for fragile samples. You tend not to break things that are only weakly associated. And then another benefit of FFF is that focusing step where we inject fluid from both ends and force the sample down onto a line. This is actually super desirable when you have a low concentration but a high injection volume. So there are applications, for example, from environmental testing, where you have a large sample and you can concentrate it onto the channel, and then you can start the elution. And the other nice thing about this is it's relatively minimal sample prep, because if there's a fairly large particle, it's going to feel a very large force and a very low diffusion, and it'll slam down onto the membrane, and it'll essentially stay there until the very end where you turn off the cross flow and then let it elute. So minimal sample prep in terms of pre-filtering your sample. Now, its strength is also its weakness. And historically, one of the problems with FFF has been too many knobs. There's all these different flows to adjust: the cross flow, the field, the time of focusing, and so on. And historically, that has probably been its Achilles heel, and we've worked really hard to try to simplify it and simplify the method development and minimize the amount of expertise required. There were also just practical issues. Early instruments were not very well engineered. They required very complicated assemblies. And I remember when I first started in this field and people showed me how to assemble an FFF channel, and they said, oh, you take out your torque wrench and you screw the top to the bottom and with a star pattern, and you adjust the torque to make certain that the left and the right are well balanced. I was thinking, why in the world do analytical chemists need torque wrenches? And one of my personal goals, has been, let's eliminate that and just make it easier to open the system, put in a new membrane, and close it with a minimum amount of effort. So no more torque wrenches. I'll talk about that in a second. So this is what an FFF mol stack looks like. It uses an analytical system, chromatography system, as the sample handler. So we have solvent reservoirs, pumps, degassers, autosamplers. Typically, we use the UV detector that's in a chromatography stack, although that's not strictly required. And then it's coupled to an analytical chain. In this case, the Eclipse fractionator that drives the fractionation on the channel, and then the sample goes in, after it's been fractionated, goes into a multi-angle light scattering instrument and a refractive index detector. It's collected with our Astra software and our vision control software for doing the fractionation, and that does the separation and the analysis in one integrated system. So the state of the art in 2020, when we started the development of the Neon Eclipse product, was to try to really simplify and rethink about, why are people doing things the way they're doing. We had the luxury of asking questions that people had not asked in a long time, which is, why are you using torque wrenches? Why are you using plastic spacers, and so on? But this is what an FFF system circa 2020 looked like. There would be a top plate, which was a flat, typically polycarbonate, transparent plate with a frame to hold it in place, a spacer that defines the geometry of the channel and the thickness of the channel. So you have a flat plate and you have a flat spacer. There was one O-ring that would seal the system together that went around a frit that acted as the support for the membrane. The membrane would go on top of the frit, which would sit in the bottom plate, and the whole thing would be screwed together with a torque wrench and star pattern to make certain everything was quite balanced. And if you didn't get the torque exactly right, then you would find that it would leak or you would have weird focusing behavior. And one of the real Achilles heel is everything were flat plates. Namely, the spacer had the seal against the flat surface, and the only real seal was this O-ring. And the torque wrench was used to seal the system, and if you didn't get the torque high enough, it would leak. But if you made the torque too high, you would distort the plastic. And part of the reason that people were using plastic is because in the early systems they would inject colored samples and they would look at the focus line and make certain the system was working. And that reminds me of the early days of chromatography where people used glass columns so that they could see the samples inside the glass columns. And of course, nobody does that anymore. People use sealed stainless steel columns, and as I'm going to show you, our new channel designs are sealed stainless steel assemblies. Moreover, the problem with torque wrenches is it's very labor intensive, and if the screw holes are not perfectly clean, you get a little salt in one of these things, then the torque that you're carefully adjusting is not clamping the channel together, just overcoming friction. And moreover, this design, it's a large area channel. When you pressurize it to 30 bar, you can have several metric tons that are pushing these plates together. Now, why is that a problem? Well, polycarbonate is a way of looking in there is great. You can see the focus line, but when you put several metric tons, it bulges. And this actually has a very practical problem in that we control the amount of fluid that goes into the channel, we control through the input, we control the amount of fluid that goes through the membrane and exits, that's the cross flow, and we infer the fluid flow that went through the detector chain is simply the difference between the two, right? It's the fluid that went into the channel minus the fluid that went out of the channel, and that makes perfect sense, except that it's wrong. And the reason it's wrong is once you pressurize it and this channel starts to bulge, it creates spare volume, and some of the fluid that goes into the channel fills up that new volume. And then later, as you reduce the cross flow and the pressure in the channel decays, then that bulging goes away and it forces fluid into the detector flow. The net result is you don't know the detector flow very well with channels that use this sort of legacy design of plastic top and plastic bottom plates. And it also means if you don't know the detector flow, or you think you know the detector flow, then when you try to compute things like recovered mass, if the flow isn't what you expect it is, you get inaccurate recovered masses. And I've seen legacy instruments report recovered masses of 120%. In other words, they're creating sample, which clearly is nonsense. Okay, so this is what a modern channel looks like. We've designed it so it's all steel construction. The channel is no longer defined by a spacer, so there's no spacer at all. It's a machined detail in the upper plate, and it's sealed with an O-ring on the top, and then there's a secondary seal that goes around the channel to seal it against the room. The nice thing about this design is that the top screws straight onto the bottom, so that with these torque wrench design, there was always a gap between the top and the bottom, so you can float the torque wrench on the spacer, adjust the screws so that it's floating on the spacer. This one, this metal surface touches that metal surface, metal to metal, so you just drop a membrane in here, tighten up the screws, and that's it. It doesn't leak, it's extremely reproducible, it's extremely rigid. We do a pressure drop test where we seal it at 30 bar and check it after 30 minutes and make certain that it hasn't changed pressure by more than 2%. And typically it's substantially less than that. So no bowing, very rigid, and very simple to assemble. And no torque wrench, just screw it down until it's tight. The other nice thing about design is it's solvent universal. So we can use the same channel for organic solvents as for aqueous solvents. And it's very gentle on the membrane, because the only thing that's touching the membrane is this O-ring that defines the channel. And so it's a rubber pressing on the membrane. So we've been able to use membrane materials that are fragile and historically would crack when you used a traditional spacer design. This one's very gentle. The other thing we thought about is temperature. Now, historically, people had put FFF channels into column ovens or large ovens to hold them reproducible, but the vast majority of the systems looked like this. They would sit on the table, exposed to the air conditioning, and the question is how good or how bad is this? And it's bad. So I took this data early in the development of this product, and I ran it overnight, and I got beautiful clumped data and overnight, and then the next morning I got very beautiful clumped data as the AC turned on and all the peaks shifted around. And it was clearly a temperature control problem. So we thought about this and thought, how can we make a system that temperature controls this but doesn't consume a lot of bench space? Because we know that You have a chromatography stack and you have an analytical stack, and you don't want to have bin space allocated to a big column oven. And so this is the solution that we came up with, is because the channel is now all metal, it's good thermal conduction to the fluid, and so we integrated into the bottom of the channel assembly a temperature regulator. And so this little block will hold the entire channel assembly stable to 0.1 degrees C in the room, even with the air conditioning blowing on it. And it operates from ambient to 55 degrees C. You can put the whole thing in a refrigerator if you want to go below ambient, but it's very stable just sitting on the channel. And it works because now every material in here is a good thermal conductor. So if I have this thermal regulated block and this has a large thermal mass, I have very low thermal gradients along this channel. And because it's the same size as the channel assembly, it takes up no bench space. And for good measure, one of the failure modes that we found was most common is people would forget to tighten a fitting and they'd get a little leak. And what we decided is to address that by putting this little thin film leak sensor on the temperature regulator channel. So if fluid leaks over the end, it makes a warning, and then if no one's there to correct the warning, eventually it'll escalate to an alarm that will shut down the pump, so you won't come back the next morning and have a big puddle in your lab. And it makes a huge improvement in data quality. So here's an overlay of 47 replicates of BSA run over a long weekend, regulating the channel at 30 degrees C. Now the dwell time of the channel is only a few minutes, so there's essentially no degradation of the sample during that time. And now you can see they're very tightly bunched. There's a tiny little evolution here, and if you zoom in on this, that's due to the membrane aging. Very good reproducibility, very good overlays. Okay, so we've simplified the channel assembly, we've simplified eliminated many of the corrosion issues, and now we've eliminated thermal drift problems. So as I mentioned earlier, there's a strong overlap between both FFF and SEC for molecules that are below about 50 nanometers. So it raises the question of why don't you just do both? And indeed, our flagship instrument does both and allows you to make one run with the FFF and then isolate the pressure component so that the next run can be run at a high pressure SEC elution. And this allows this instrument to do both orthogonal fractionations. You can do both FFF and SEC of the same sample, and that maintains the ability to compare to historical methods, especially for validated applications. And so here's an example of what that looks like. So here's an elution of BSA, and first the monomer comes out, and then the dimer is because it has this small and then large elution. And the next run was an SEC run, and of course it's inverted relative to FFF, so the dimer comes out first, followed by the monomer. The next issue is the concentration of the sample after it's fractionated. As I showed in the early description, all of the separation happens very close to the membrane surface, so approximately within 10 microns. And the channel may be 500 microns tall. Now, if you think about what that means, the sample is way down here at the bottom. And at the end, we're going to be pulling that into a detector port. And we're going to be mixing it. All of this fluid up here is all just pure solvent that just goes along for the ride, essentially just carrier fluid. And if we take all of this carrier fluid and we put it in the detector port, we're going to dilute the sample by roughly 50 to 1. So there's an old idea of making a separate port that can skim off the pure solvent that's in the top of the channel and separate it from the sample, which is really right here at the bottom streamline. And so our implementation of this idea is called the dilution control module. We've optimized it so that we have very good separation. We don't, for example, take any of the sample and have it go into the DCM port. The sample all ends up in the detector, and we get minimal loss of resolution when we do this. And the net result is, if I can take most of the sample off, let's say I take, 2/3 or 3/4 of the solvent rather in this area and bring it into the DCM port, the net result is there's less dilution that happens at the detector, and you see the concentration at the detector port go up. So we call it the dilution control module because we're really reducing the dilution or effectively increasing the concentration in the detector port. Now the question is how to do this. And the most obvious way is we said that the current system has one pump that brings the fluid in, and then a series of flow controllers that control how the fluid exits the port. So there's the pump that brings the fluid in through the inlet port or the inject port for where the sample comes in. There's a flow controller that controls the cross flow. The most obvious thing to do is just to put a flow controller on the DCM and then control that, and then the detector flow would be what's left over. And in fact, we tried that, and it almost worked. It kind of worked, but it had a problem. So here's the problem. We want a reliable detector flow. And we're going to define that as the difference between the flow that went into the channel on the inlet port minus the fluid that left the channel through the cross flow port and minus the flow that left the channel through the DCM port. Okay? Why is this a problem? Well, imagine that we want this ratio to be 9:1. So that this is 10% and this is 90%. And furthermore, imagine that you can control these flows, like the inlet flow from the pump, to an accuracy of 1%, and you can control the cross flow and the DCM flow also to 1%. And ask how well can we control this split ratio? Because that controls how much of the concentration enhancement we're going to see at the detector port. So a typical experiment might look like this. Inlet flow would be 4 ml per minute. The cross flow might be 3, and to get this 9:1 ratio, the DCM would be 0.9 and the detector flow would be 0.1. And that would give us this ratio that we were wanting to get of 9:1. Okay? Now let's do the worst case. Take the inlet flow 1% high and the cross flow and DCM flow is 1% low. And now 1% high is 4.04, 1% low on this one is 2.97, 1% low is 0.891. Oops, the split ratio is now not 9:1 like we wanted it to be, it's only 5:1. And let's take the worst case in the other direction. Remember, we're controlling everything to 1%. That's not bad control. And it gets even worse. 1% low, 1% high, and now our split ratio is 43:1. The net result, if you control this flow, the DCM flow, and the cross flow, you have very poor control on the ratio between the two. So we don't do that. In fact, what we really want to do is we want to control the detector flow. So let's do that. And this is the control mechanism that we came up with. So don't control the DCM flow. Control the detector flow. And how do you do that? The analytical instrument chain is on the detector flow. So here's a little cartoon. The sample comes out through the detector port and it's going to go into the detector chain. But then where does it go after that? It's going to go into waste. So before it goes into waste, we run it through a flow meter. And here we don't really care about mixing up the sample because we've already run it through our analytical instrument chain. But now we can figure out what is the flow through this. And let's say we want to control the flow in my previous example of 0.1 ml per minute in the detector flow. And I measure it and I find it's 0.8 or 0.08 instead of 0.1. So it's too low. So the way I can increase the flow is not by controlling the flow here, but by controlling the pressure within the channel. So we take the DCM port, we run it into a pressure controller, we then increase the channel pressure, and that increases the pressure across the detectors, and that drives more fluid through the detectors. And so we do that until we get the desired detector flow. So we have this hybrid control scheme of we measure the flow, we set the channel pressure, increasing the channel pressure until we get the flow that we want, and then we hold it constant. And then the sample goes through to waste. This alleviates that problem of not knowing what the detector flow is because we're controlling it directly. So we get precise detector flow. The consequence is all of the analytical instruments perform better when the detector flow is very stable. So we get more stable detector baselines, we get accurate recovered mass calculations, and because we're measuring the flow after it's been through the detectors, we don't affect the analytical measurement at all. We see no additional band broadening. And the error accumulation now shows up as a tiny change in the DCM flow, which is much less critical than a tiny change in the detector flow. And so we filed a patent that was granted on this control mechanism. And it makes all the difference in the world. So this is how well it works. We define this parameter we call the contrast enhancement, or the concentration enhancement. So if I have all the sample going through the detector port, I get some level of dilution. If I can pull off 50% of the fluid and send it through the DCM port, and 50% and send it through the detector port, then I should see the concentration enhanced by a factor of 2. So the ratio of the DCM flow to the detector flow plus 1 is the concentration enhancement. So here, concentration enhancement, factor of 2, 3, 4, 5, and so on. You see the peaks get higher and higher. Now, at very high concentration enhancement, we're making these this 10 times higher. We see a little bit of loss of resolution, but mostly we just see an enhancement in the signal. Now, how do we know that we're not losing sample through the DCM port? Well, we do the following experiment, is we integrate those peaks, and we look at the normalized peak area as a function of the concentration enhancement, and you see it's perfectly linear. Namely, we really are just pulling off solvent in the DCM port and losing no mass through this port. Okay, so it really works, and it means we can meaningfully get 5x, 10x improvement in the sample with minimal loss of resolution. Another consequence of controlling the detector flow is improving the detector baselines. For example, the refractive index detector is well known for being very sensitive to the flow through the detector. So if you have small variations in the RI flow, it shows up as a wander in the RI baseline. And so here is an example of when you use the RI detector with a large number of replicates. Here we get, again, tightly bunched 50 replicates with good overlay, and then overlaid here is a blank, and you can see the blank has a very little deviation from the sample runs. And we typically always run a blank run and subtract it to do a blank subtraction, but when you have very good detector regulation, the need for the blank subtraction is reduced. I mean, we still do it, but it makes much less of a correction. One thing you'll notice here is, although the membranes that are used for this are typically ultrafiltration membranes, they let the solvent through but not the sample, they do retain some salts. So typically you see in the focus state a different salts level that shows up as a baseline shift than when you're in the elution state. And so this jump is quite common, and this means that the membrane was actually retaining a small amount of salts. And by having a well-defined detector flow, we get a well-defined baseline even with this salt shift. Now I'd like to discuss another option to the FFF channel called the dispersion inlet channel. And the idea goes back to Cal Giddings and Myung-Hee Moon in 2001. And the idea is that the focusing channel pushes the sample off the top plate down onto the membrane by applying a focusing flow that goes both from the inlet and from the exit. And that works very well for concentrating the sample onto the membrane and making a line. But it's complicated in the sense of you have to have a series of state changes. There's one state to inject the sample during focusing, there's another state change to pure focusing, and then there's another state change to elution. And each one of these state changes requires valving and changes to the system that can cause little pressure pulses that could potentially upset the very delicate equilibrium that's been created right near the surface. So the idea of this new method, or it's an old method that we've re-implemented, is that if you have a secondary flow right near the inlet, when the sample comes in, of course it fills from top to bottom, but instead of relying on the focusing to get it down onto the membrane, the secondary flow, you can think of it as like a shower head that pushes the sample down onto the membrane. So this happens as a continuous process that they called hydrodynamic relaxation. And the nice thing about it, it's very much like SEC. You just set all of these flows. There's no state changes, and you simply inject the sample, it gets pushed down, and then it starts fractionating as it moves down, and then it's collected on the exit. Now this has a number of benefits. It's very simple. It minimizes any interactions or on the membrane or overloading artifacts. The focusing is so efficient that sometimes you can create a very high concentration and you can induce aggregation, and this is free of all of those issues. Now the downside is you lose some of the benefits of the focusing channel, namely you can't concentrate the sample on the membrane. You have to inject a small aliquot of the concentrated sample, and because you don't get that nice straight line where all of the runners lined up at the beginning of the race, you get slightly lower resolution. This is our design that we call a frit in a frame design. So we have an inlet region where here's the frit that's going to cause that flow that pushes the sample down from the top to the bottom. And we press it into this little cavity, and then we screw it into the top plate with these screws. And then we put it in the spacer, and then the spacer covers up and seals all the screws. And the net result is the sample comes in here, it goes over the frit, and it gets pressed down onto the membrane, and then when it exits the frit, the elution starts, the fractionation begins. So this is what it looks like when it's assembled. So there's the frit in the frame, there's the spacer, sample injects, and it goes down the channel. And then here's our DCM port and our sample collection. How well does it work? So here is the dispersion inlet channel, showing the percentage of the sample as a function of size, where I've converted now the fractionation of BSA into the monomer dimer. And here's the focusing channel. And indeed, the focusing channel has slightly better resolution. You get slightly better plate counts, but the difference between the DI channel and the focusing channel is pretty small. And so the simplicity trumps for most cases, trumps the benefits from the focusing channel. So this has become a very popular alternative to the focusing channel. They both have their roles, but this is seeing more and more use because it is so simple. Along that theme, we just want to make the rest of the use of the system equally as simple. There's a lot of interaction with the membrane. You have to open up the channel and replace the membrane. So we've made that very simple. Unscrew it, drop the membrane, screw it down. We also want to make certain the plumbing is equally simple. There's a lot of fluid fittings that come to and from the channel. So we've color-coded everything, like blue goes to blue, red goes to red, yellow goes to yellow. So basically, anyone can assemble these things just by matching all the colors. We've added smart solvent management. FFF systems tend to use a lot of solvent, so when you're flushing a channel, you want to automatically recycle it, and when you're running your measurement, you want to switch to waste. So we've added these waste recycle management inside the instrument, and it can be programmed as part of the method of when you can send the sample or the eluent to waste and when to recycle. So that minimizes the amount of solvent. All of these things go a long ways toward making these things a lot easier to use. Added a lot of UI improvements. You can see at a glance how well are the flows being regulated. You can see during the method the peaks coming out. You can see the programmed flows being regulated. So this is the desired method. Here's the actual status as it's regulating. It should follow this along the lines. So basically, at a glance, you can see what the system's doing. We have health indicators that show whether or not the detectors are stable, whether or not the flows are regulated. Really just try to make it as straightforward as possible. Let me make a slight detour and talk about one alternative method of measuring FFF that we've seen in increased use in the last few years. This was again pioneered by Christoph Johann. And it's the idea of combining flow FFF with an applied electrical field. And this allows you to improve the fractionation by doing partial fractionation based on charge and partial fractionation based on size. And so the basic idea is the following. If you have no electric field and across the channel, and you just have the flow through the membrane, you get the normal asymmetric flow fractionation, namely separation by size. The field comes entirely from the interaction between the flow and the frictional force on the particles. But now imagine that I turn on an electric field and the particles are charged. Well, now the electric field can either force the particles more firmly toward the accumulation wall, or they can lift the particles away from the accumulation wall so they're pressed less firmly. So if the electric field is in the same direction, makes a force that's in the same direction as the flow, then you're going to retain the sample on the membrane longer, and you'll see it retarded. Or if the electric field is reducing the force against the membrane, you'll see it advanced. So the peaks will occur either early or late based on their relative charge. So you make a run with no charge, you make a run with the electric field applied, and look at the change in the relative arrival times. And that gives you a measure of how strong of a flow you're inducing by the field. and that is a measure of the electrophoretic mobility. So this is what it looks like. The channel is a titanium-based channel with a platinum coating. We've also made a fixed height variant of this one. We have platinum plating on all the wetted surfaces, and then we oxidize that titanium, the holes through the ports, so they effectively are encapsulated by titanium dioxide. So the only field-bearing surface is the platinum. We can apply up to 30 milliamps, plus or minus 30 milliamps across the channel in addition to the flow through the membrane. And that corresponds to a field strength of up to 75 volts per meter. And so this is what the data looks like. So this middle run here is an elution with no field applied. So this is 0 milliamps. And you can see this is a carboxylated polystyrene latex that's 60 nanometers. It's highly charged. You see you get a nice peak. Comes through. We did 3 replicates. The replicates overlay beautifully. Then you apply a positive field, in this case plus 3 milliamps, and the peak is retarded because it pushes the sample more firmly toward the membrane. So instead of the peak arrival time being about 14.6 minutes, it shows up at about 16.8 minutes. And when you change the field to the opposite you make the opposite current, so minus 3 milliamps, then you see it's advanced. So this time shift is a measure of the flow that's being driven by the electrical field. And so you can convert that to a drift velocity as a function of the electric field strength. And so this is no field, this is the positive field, here's the negative field. A fit through this line measures the electrophoretic mobility. So in this case, we get the size based on the 0 field, and we get the electrophoretic mobility based on the peak shifts. And in this case, it's minus 4 mobility units, which is 10 to the minus 8 meters squared per volt second. Okay, so this is a way of measuring electrophoretic mobility, but one of the nice things about combining it with the fractionation is, one, you can fractionate out aggregates, or if you have... Okay. So with all of this, there's control software that allows you to set up the methods and monitor the elution as a function of time. This is our Vision Run software. It's integrated with the Waters ARC HPLC system, so you can use the quaternary pump, the sample manager, the PDA detector. You can watch and control the flow through the channel. And on the method development side, we have the Vision Design software where we simulate the FFF theory for our channel, and you can do a virtual experiment by applying a method and telling it what sample sizes you want, and it will say, okay, based on this method, this is the fractogram that you should expect. And this allows you to optimize your methods before you run them, or to take a method that's already been run and adjust it to get better resolution or to reduce the time of fractionation. So it's a super valuable tool for ahead of time optimizing methods so you don't have to do so much experimentation. And finally, we get a lot of questions on whether or not this technology is really robust enough that it can make the transition from analytical labs into quality control applications. So we've done this following experiment. Is if you want to replicate a system across multiple sites, it's really critical to get consistent performance from unit to unit, and of course, even more important, to get an assembly-to-assembly reproducibility. So this experiment, we took a series of short channels of different manufacturing by different dates, and we ran them with a nominal 350 micron nominal height. And one of the parameters that we use for characterizing the elution is to use the theory to determine what the effective channel height is, because the membrane itself can crush a little bit, and it's it's a squishy material. So we can define the effective channel height based on the elution time that's measured and the theory applied to that to ask, okay, if it was exactly 350, the peak would arrive at 8 minutes, but it arrived at 7.5 minutes. So in fact, the channel must have been 345 microns. So that's what we define as the effective channel height. So we did a series of experiments of reproducing unit to unit And for this system, we got a 308 nanometer. This is almost certainly due to the thickness of the membrane. But we saw a 5% variability from channel to channel across multiple channels. And really critically, when you take one channel and you open it and just replace the membrane, you see a reproducibility of better than 1%. And that's probably just the limit of how reproducible the membranes themselves are. So this says that it really is to the point where it's reproducible enough that you can replicate results across multiple sites with multiple independent systems. So we've spent a lot of time and 30 years of experience reimagining how we can simplify FFF. And the goal is to really make it a simple, reproducible, and practical technique where you don't need to be an expert to be successful. And a lot of things that we've done, like technical improvements, regulating the detector flow, controlling the temperature of every channel, having a dilution control that allows you to get a high concentration of your sample in the analysis chain, being able to switch back and forth between FFF and SEC so you can make contact to historical data. We have very good fraction collector support, and the fixed site channels really resolve many of the pain points of how do you open the channel and replace the membrane and really get highly reproducible results. We have a wide variety of different channels, long and short, to change the amount of sample and the speed of the collection. Semi-prep, you can do much higher sample loads, the mobility that allows to measure electrophoretic mobility, the dispersion inlet, which really simplifies the method development and acts a lot more like SEC. And of course, the resulting system is tightly coupled with our analytical instrument chain. You can do FFF, multi-angle light scattering, UV-RI, even viscometry. This allows you to do things like conjugate analysis of macromolecular assemblies, to look at protein carbohydrate complexes. You can look at lipid nanoparticle distributions and their loadings, and a wide variety of applications.